Okay, we are going to work problem 6.47 together at this point. Another fun problem in thermochemistry. What we got going on here is we are going to actually mix a strong acid with a strong base inside a device called a coffee cup calorimeter and run a chemical reaction. It's going to be a neutralization reaction. So we're mixing 25 milliliters of 0.5 moles per liter sulfuric acid with 25 milliliters of 1 mole per liter potassium hydroxide inside this coffee cup. The initial temperature is 23.5 degrees. The final temperature after the reaction occurs is higher. It's 30.17 degrees Celsius. And what we are asked to compute is the delta H, triangle H, which is the enthalpy change of reaction in kilojoule per mole units of water forms. So we want to know the enthalpy change associated with the formation of the enthalpy change associated with the formation of 1 mole of water in kilojoule units. Now, where do we go with this? My goodness, we have got lots of things going on, okay? The first thing that I'm going to recommend that you do, and if you're faced with a problem like this, which I might call a quantitative calorimetry type of problem, is write a balanced chemical equation for the reaction. Now here it's an acid-base neutralization. We know in that reaction class or category from a previous chapter that if a strong acid reacts with a strong base, you make water and a salt. So we got the sulfuric acid, a diprotic acid. It's got 2 protons that can be donated, reacting with 2 copies of KOH to make 2 waters and 1 of the K2SO4, the potassium sulfate. Now, as I've written this, it's balanced, but you'd have to predict the products of that reaction, and you'd have to balance it yourself as a first step, okay? Now, where do we go from here, okay? Well, I'm looking at the problem. It seems like I have some information about temperature changes. Maybe I can compute a heat flow, and I'll get to that in a second, but I really want to know how much heat's produced per mole of water that I make. So not only do I have to consider the heat flow part of this problem, I also need to know something about how much of my substances are going to react, okay? So what I'm going to do is I'm an analytical chemist at heart. I like to be pretty quantitative whenever I can. So I'm going to build an inventory, what I like to call an inventory, of all the substances present and then what happens during reaction. Okay? I call this my inventory. And the first part of my inventory is the number of moles that I'm adding into my reaction system. Okay? That goes for the acid, it goes for the base. Separate substances, right? So let's think about this. Well, if I wanted to figure out how many moles of H2SO4 that I added, how can I do that, right? I mean, I'm told that the concentration is 0.5 moles per liter, the volume is 25 milliliters, but how do I figure out how many moles of H2SO4? Well, that's hopefully pretty easy for you. Remember earlier I told you that there's this equation. If you ever need to figure out the number of moles of a solute, here the H2SO4, that's dissolved in an aqueous solution. What you do, you take the molarity, here that's 0.5 moles per liter, that's in moles per liter unit, and if you multiply that by the volume of your sample in liters units, here that's 0.025 liters, because I had to divide my 25 milliliters by 1,000 to convert to liters. But if you do molarity times volume in liters, that gets you moles. Moles of the material present. Okay, it's a very, very important equation for you to remember. You're going to use that all the time in your chemistry class. Molarity times volume. Now, if you do that math, you find that we've added 0.0125 moles of the acid. Okay. Now, what about the other substance, which is the KOH? In a similar fashion, I can figure out how many moles of my KOH are present. The numbers are a little bit different there. but I'm going to use the exact same equation, okay? So it's for KOH, which is a strong base. I've got 25 milliliters again, which if I convert to liters, is 0.025 liters. But I need to multiply that by 1.00 moles per liter because my molarity is different. It's twice as big, okay? So as a result, if I'm doing my inventory of how much base I've got 0.025 mole of my KOH initially. Now this is what I'm adding, I'm mixing together inside of my coffee cup, which is going to be my reaction system. Okay, now once these acids and bases mix, we know that acids and bases like to react with one another, to neutralize one another, to form water. Okay, so the next question is how is the situation going to change from this initial condition? Okay, how is the situation going to change? Well, strong acids and bases like to react completely to make products. They consume as much as each other as they possibly can. So this kind of becomes a limiting reagent problem for us then. What are we going to run out of first, right? Now in this particular problem, it's a 1 to 2 stoichiometry. And it looks like I've got exactly twice as much of this, the base, as I do the acid. Okay? So what that basically means is my change that I can predict is that I'm going to have a negative 0.025 mole loss of my base, and I'm going to have a loss of half of that from my acid. The reason why it's different is because I need 2 of these for every 1 of these. So if I had 1 mole of this, it would require 2. So I need to use double of this compared to what I have of this. But it just so happens in this particular case that I'm lucky because I've got exactly the right amounts to consume both of them. It doesn't have to be the case. I could have given you a problem where that's not true, but in this particular case it is true, okay? And the beautiful thing about that is all of the acid reacts, all of the base reacts, and in my final position of my inventory, so I've got how much I added, how much it changes, and then how much I have left, my final, I've got none of this and none of this, okay? However, my chart's not completely done yet. Because remember, I need to know how much of this stuff that I make for the work in the problem, right? Well, I'm going to have some of this originally, okay, because it's the solvent, it's a liquid, it's floating around, in these solutions, okay? But the thing is, what I care about is how much I actually make here, okay, as a result of this reaction. Now, if it's a 1 to 2 to 2 to 1 ratio, doesn't it make sense that the amount of water that I make will be 0.025 moles? I might call that 25 millimoles. And then as a result, that's how much is going to be produced. So that's going to ultimately be a key number to me, because that basically tells me how much water that I have made as a result of this reaction, okay? It's the same amount as this because the stoichiometry is here too, okay? So the stoichiometry works out. So now I know that when I mix the acid and the base in this coffee cup, I know exactly how much water I made, 0.025 moles, 25 millimoles. And the heat that was generated as a result of this reaction comes from that amount of water being made. So 25 millimoles of water being made inside my coffee cup causes the temperature to rise from 23.5 to 30. That's what's responsible for this temperature rise. So we're kind of making some progress here, but we're not completely done yet. Because now I need to know how much heat is generated in my reaction system, my Q term. Now remember, if I'm computing Q, take my specific heat, and I can multiply by M, my mass, and multiply by my delta T, my change in temperature. I'm going to use that here to help me figure out how much heat was required to raise this solution to the temperature that was specified. Now, I'm dealing with aqueous solutions here. I'm told in the problem to assume the specific heat is the same for water, which is 4.184 joules per gram per degree Celsius. So I'm going to write that here, Okay? I was told in the problem to do that. Now I need to multiply that specific heat by mass. What mass should I use? Okay, well, I'm going to argue that the mass that we should use here should be 50 grams. The reason why is because to generate the reaction, we mixed the acid and base inside this coffee cup. Okay? We had 25 milliliters of each. We're also told the problem that we could assume the density is 1 gram per milliliter. Okay? So if that's the case, this is 25 grams. This is 25 grams. You add it together, conservation of mass, right? And you get 50 grams. Okay? So 50 grams of solution. Now the only other thing that I need to multiply that by to figure out my heat that's generated is my temperature change. My final temperature minus my initial. I was told in the problem the final temperature after a reaction was 30.17 degrees Celsius. The initial temperature was 23.5 degrees Celsius. So the good news here is I have every number that I need to know to compute how much heat was generated to cause this temperature to rise. And if I do that calculation on my calculator or computer, I get 1395.36 joules of energy was required to raise the temperature to 30.17 from 23.5. Okay? So this is how much heat energy was associated with the temperature change. I should also say that you may be a little unfamiliar with this device, this coffee cup calorimeter, but you might see this in lab. Okay? It's a really common way to study heat exchanges in this thermochemistry business. It's really simple. All you do is you take a coffee cup. Sometimes there's 2 coffee cups that are inside each other. That's to present, they're made out of styrofoam. That's to basically insulate this reaction system from the outside really well. And then all you do is you take a thermometer, put that down in the solution. You can measure the initial temperature, the final temperature. You can get your temperature change, and you can even measure the mass of the solution with the balance if you want. And then you know this number because it's just the heat capacity of water. It's a really useful device for measuring heat flows or enthalpies of reaction. And the really cool thing about it is sometimes you'll put like a little cardboard cover here, but it's not really airtight. So you're actually doing constant pressure calorimetry here because the atmospheric pressure is always the same, which means that we're actually measuring our enthalpy change when we do this, because by definition, your enthalpy is the heat flow at constant pressure, okay? So we're actually measuring our delta H. Now we're not done with this problem, okay? We know how much water was made. We know how much heat was generated based on that amount of water being generated or made. If I increase the amount of water being made, I'll increase the amount of heat being made, okay? If I double that, I would double this. If I multiply this by 4, I would multiply this by 4, okay? So the point here is that these two scale together because this reaction generates so much heat per mole of water. Now we need to figure out what that is, okay? So it seems like we got over 1,000 joules of energy already. So why don't I just move the decimal place 3 spots right off the bat here, make this 1.395 kilojoules of heat that's produced per 0.025 mole. And if I want to compute my delta H on a per mole basis, it's pretty easy to do from here because I know that I generated 1.395 kilojoules of heat energy. Decimal place is right here. Per every 0.025 mole of water that was generated. So I just have to do the math. Turns out if I do that, I get 55.8 kilojoule per mole. And since the temperature rose during the experiment, we know the reaction's exothermic, and it should be associated with a negative sign. Okay, so oftentimes it's said that the heat of neutralization to make a mole of water is about 55.8 kilojoules per mole. It's an exothermic thing, so it's negative, right? So this problem just basically goes to show how one could do an experiment to actually measure that, and maybe you'll get an opportunity to do this type of thing in lab, okay? But it's a fun problem because it combines elements of stoichiometry, solution stoichiometry, the amount of material present, and then also combines elements of this chapter on heat flows. So it's kind of a quantitative calorimetry type of experiment. It's a little bit fun. I think these are kind of cool problems.